I'm now interested in obtaining shortcut formulas for the derivatives of trig functions. So for instance, what is the derivative of sine? Now I could do a little bit of preliminary detective work here. And so what I mean by that is if I were to take the graph of sine, and let's just say 1 period, I take a look at it and I can see that it satisfies the necessary condition to have a derivative. It's continuous, no holes, no gaps, no jumps, no breaks. But moreover, when I look at its graph, I don't see any pokey things, no corners, no cusps, no sudden changes in slope, nothing bad of that sort. So I'm also suspecting that it should have a derivative. So I could, underneath, sketch an axis where I talk about the slope of that function. And then I could go through this exercise and say, look, if I were to draw a little tangent line there, the slope would be a positive number. And the slopes become the y coordinates over there. So I would see a positive slope. As I move through to the next point, the slope is still positive, but it becomes a bit flatter, so a bit less steep. I have a 0 slope right at this point. I have a negative slope, and it looks like it becomes most negative somewhere around here. And then the slopes want to become more positive till they get back to 0. And then once I start repeating, they rise up again. So if I were to connect the dots, it almost looks like some sort of cosine. So I really want to know, is it a cosine? So what I need to do is use the definition of the derivative in order for me to actually determine what the shortcut formula would be. So I write out the definition of the derivative. So that means according to the derivative, I'd have the sine of x plus h, subtract the sine of x, all divided by h. First thing I should do is sneak a peek. So no limit laws whatsoever. And I should do some algebra here to try to fix it. Now, at a rule of thumb, the algebra kind of depends on the worst part of your expression. This thing is the ugliest part, and to deal with this, I'm going to end up using a trig identity. That's why we make you take all those pre-calculus classes, so you can learn this kind of stuff. Now, you've most likely forgotten what this identity is, but it turns out to be the sine of x times the cosine of h plus the sine of h times the cosine of x. I'm going to take that expression and plug it in to the definition of the derivative for that term in the red box. So I'll have a sine of x times a cosine of h plus cosine of x times the sine of h, subtract the sine of x, all of it divided by h. You say, oh, it looks so much worse. What do I do now? Well, just basic algebra type stuff. There are two terms that have a common factor, so I'm going to group them together. It's always handy to group things and see what you get. So if I were to group the first and the third term, the common factor would be sine x, and when I remove it, I would see a cosine of h minus 1. And in the second term, I'd have a cosine of x times the sine of h. Now, this entire thing is over h, so it's one big fraction, but it's up to me if I want to split it. And so I do in this particular case. I'm going to split it as two separate fractions. And then even more so, I'm going to write it in this suggestive way. I'm going to write it as the sine of x times the cosine of h minus 1 all over h, cosine of x times sine of h divided by h. I'm going to group together all the things with h and separate them in some way from the things with x. I think I've hit the end of the line algebra-wise, so I want to know if I can use the limit laws. Do all the inside the constituent limits exist? The limit variable is an h, so all of these limits without any h's exist. They're constants. And now I'm hoping you can see why we bothered studying trig limits earlier. We know that the limit of sine h over h as h goes to 0 is 1. And we also studied this particular limit, that the limit as h goes to 0 of cosine of h minus 1 all over h is also 0. So all of those limits exist. And because they all exist, I'm going to apply them. So I'll get the sine of x times this limit added to the cosine of x times this limit. So it ends up giving me a nice result. Sine of x times 0 plus cosine of x times 1. And I come up with a shortcut formula for this derivative function. And it agrees with my picture. The derivative of the sine function is cosine. And that's exactly what I thought I saw with the picture from earlier. Now, you're going to do a similar thing for the derivative of cosine. And the only difference being is that the identity you're going to use is slightly different. You're going to need a cosine of x plus h is cosine of x, cosine of h, subtract sine of x, sine of h. But when you go through that exercise, and I recommend that you do, you can write this out and do exactly the same steps. You're going to end up getting the derivative of cosine is negative sine. Now, this is also a special moment in the course because we've got enough in the way of tools and rules to be able to start coming up with more derivative shortcuts without the limit definition. For example, if I wanted to take the derivative of the tangent function, remember that tangent can be defined as sine of x divided by cosine of x. And so I could then pose this question as saying, what is the derivative of this quotient? And if you've been doing your homework, you know that you can use the quotient rule. And so using the quotient rule, you take the derivative of the top multiplied with the bottom, subtract the top function multiplied with the derivative of the bottom, all over the bottom function squared. And what we are doing is now building upon results we've already come up with. We know the derivative of sine is cos. We know that the derivative of cos is negative sine. Downstairs, we are going to use this notation that this is really cos squared of x. Those two things mean the same thing. It's just the convention that is used. What we're going to end up with is a cos squared of x plus a sine squared of x, all over cos squared of x. You should know that this is equal to 1, positive 1, sorry. And that means you are able to simplify this expression. It's 1 over cosine of x with the square. Now, if I wanted to, I could write this as 1 squared over cos squared, which I could write as 1 over cos squared. This is what the definition of secant is. So the standard convention with differentiating trig functions is that we write them as simple as possible. So in this case, the derivative of the tangent function is secant squared of x. Now, similarly, the cotangent function is defined as cos x over sine x. And if you use the quotient rule again, and you go through exactly the same steps, the derivative of cotangent is going to be negative cosecant squared of x. And cosecant squared of x is defined as 1 over sine. If I was asked about the derivative of secant, I just showed you a moment ago that this is 1 over cos. So again, we use the quotient rule. Derivative of the top times the bottom, subtract the top times the derivative of the bottom, all over the bottom function squared. What's convenient here is that the derivative of 1 is 0. So I'll get 0 subtract negative sine of x over cosine squared of x. So this is sine x over cos squared x. Now, the derivative rules, the standard convention is that we don't write them in terms of fractions like this. So we are going to go one line further and write this as sine x over cos x times 1 over cos x, which gives me secant, or tangent in this case up front, times secant. So you end up with another handy little rule. The derivative of secant x is secant x times tangent x. And the final one is that if you wanted to take the derivative of cosecant x, it would end you negative cosecant x times cotangent x. Oh, those are all so messy. I'm supposed to memorize that? Oh, that's too much. Okay, well, here's a way for you to try to remember it. I'm going to write all the functions that do not have a co on one side. Sine, tangent, secant. These ones you have to remember. There's no way around it. So you're going to get an answer here, cosine, secant squared x, secant x times tangent x. Now, are the other three, they are all what are called co-functions of the originals. Okay, I'm hoping you can remember that the derivative of cos is negative sine. That's pretty easy. But for the other two, there's a nice little pattern. Tangent has this result. So in the other column, what you're going to do is change the function to its co-function. So secant squared x, its co-function is cosecant squared x, and then you put a minus in the front. The derivative of cosecant x, it's the same formula as the secant one, except all the functions are changed to cos, and you put a minus in the front. Now, once you've got these 6 rules, you can just continue to piggyback off things. So for instance, what's the derivative of tan theta minus 1 over secant theta? I can once again use the quotient rule. No limit definitions are required. All I have to remember is to use the quotient rule properly. So derivative of the top times the bottom, subtract the top function times the derivative of the bottom one, all over the bottom function squared. Right? But your first step is just to go through and grind through the derivatives. And so here, you end up with this kind of mess. Now, depending on whether or not you need to simplify things, you can end up with several terms. So if I were to distribute this to both terms, I'll get a secant theta tan squared theta plus secant theta tan theta. Remember, there's a minus sign in the front that needs to be distributed. Upstairs, there's a common factor to everybody, secant theta. I'll have secant squared theta minus tangent squared theta plus tangent theta. Downstairs, I'll have a secant squared theta. Conveniently, one of those secants will go away. There's a trig identity that says 1 plus tangent squared theta is secant squared theta. So that means secant squared theta minus tangent squared theta is 1. Ah, do I need to know that? Yes, you need to know that. Very important. So you end up with a 1 over secant theta times 1 plus tangent theta. Look, if you want, you could change the front function to a cosine 1 plus tan theta. But getting some level of simplification is enough.